All right, we should all be on this page. At the top, it should say arc length. Make sure you're on the right page because there's two that kind of start out the same way with some circles at the top there. So I want to make sure you're not writing down your notes on the wrong page. So make sure at the top here it says arc length. That's what we're going to talk about today. And I'm going to kind of go over two different ways that you could find arc length, either using degrees or using radians. Most of the problems that we're going to do today are going to probably be working with the radian side, just because I feel that that formula is a little bit simpler to work with, but it is possible to do this if you have degrees. So remember yesterday we'd spent some time going back and forth between degrees and radians. We talked about how they relate to each other. We even went over in your notes yesterday about the circle and kind of the four quadrants and how it makes up 0, 90, 180, 270, 360 as far as degrees go. And then we talked about what does that mean in radians. When we talk today about arc length, instead of focusing on like the degree or the radians inside the sector, I'm more so talking about the space on the outer edge of the circle. Like how long is that? So in both of these pictures here where they have that little S at, S is representing the arc length. So when we work with our formula today, we might see an S, and S is going to stand for the arc length. So when I have my formula starting with degrees, it's going to look like this. S is going to represent arc length, and that is going to be equal to the following. If it's in degrees, you would have that angle there in the corner where on my pictures right now they say pi over 2 and pi over 3. If it was in degrees, though, it would say something like 40 degrees or maybe 120 degrees. They would give you something else that's not in the radians form. In the past, when we've had angles in there, when we did like area of a sector a couple of units ago, we used theta to represent the angle. We're still going to use that today. So for degrees, you'd have theta to represent the angle. So that would be like your 40 degrees, your 100 degrees, whatever it is that they're giving you, times pi times the diameter all over 360. Remember, pi times diameter is representing the circumference of the full circle. And so the pi times diameter is going all the way around, but that theta over 360 is just focused on the portion that we're talking about. Another way you could think about this formula is instead of pi times diameter, we could have had the radius. So for circumference, we talked yesterday about how we also had the formula 2 pi r all over 360. So again, these two pieces here, the pi over diameter, pi times diameter and 2 pi r, these represent the circumference. The theta over 360 pieces, that's then talking about, well, I don't want the whole circle. I just want this portion. So the theta over 360 represents whatever portion we're talking about. So again, if your angle was 40 degrees, I would take 40 divided by 360, multiply that times the entire circumference to figure out just my little segment that I want. Okay, now that's in degrees. Sometimes, though, they're going to give it to you in radians, and that's what we talked about yesterday. How do you go back and forth between the two? Anytime that I had something in degrees, I could actually convert it to radians now and use the radians formula if I wanted to. Now, the radians formula looks similar to the degrees one. So it's going to still start out with an S because that's still arc length. And if I still keep the top the same, and I'm going to just do the second one for now, so I'm not having to rewrite it a whole bunch more times. But so I'm going to just think about the top as being theta times 2 pi r. Again, theta now this time would be represented in radians, like what we see in our pictures, pi over 2, pi over 3, 5 pi over 4, whatever it might look like, and then times the circumference. But when we think about radians, think about what we talked about yesterday. How many radians are in a full circle? It's in your notes. You just got to turn the page back. All of you should have a resource that you can use if you don't remember. How many radians did we say was in 360, Quentin? 2 what? 2 pi, right? So instead of on the bottom here being 360, I'm going to replace it with 2 pi so that it's in radian form. Now, if you guys take a look at that, what do you see is going to happen? What specifically is going to cancel? The 2 pi's. So this 2 pi and this 2 pi are gone. What are you left with then? Theta times radius. Now that happens when you're working with the radians. Okay, that didn't happen over there when I was working with degrees because I didn't have a 360 on the top that canceled out with anything. So I would say for today, most of the problems that you're going to deal with are going to have it in radians, like we see here on these 2 circles. If they do give it to you in degrees, you can work with the degree formula that I have written up there, or you can kind of combine what you did yesterday and convert degrees to radians, and then just use this simpler formula. I think out of the two formulas that I have here, this one is a little bit simpler. It's less to remember. It's less going on. There's fewer opportunities here for us to make a big mistake. As far as when you're plugging in for degrees, there's a lot more pieces. You have to remember a lot more for that formula. Okay, so I'm going to probably lean more towards using the theta times radius today. So anytime that I have degrees, I probably will take it that extra step, convert degrees to radians like we did on your bell ringer, and then use my formula. Let's do an example here. We've got these 2 circles right underneath. I'm going to go ahead and do the first one with you guys. So I'm just going to use this formula. Arc length S is going to be equal to theta times my radius. And I just need to pull those things out from my picture. I don't know what S is. That's what's marked as the variable in my circle. What do I put in for the theta? Good, pi over 3. And then what do I put in for my radius? 5. And if you would like to, like we did yesterday, you can write it as a fraction, 5 over 1. You don't have to do that if you're comfortable multiplying with fractions, but I know for some it helps to see the numerators and the denominators so that you're putting things together and like reducing if you can. I don't think there's any reducing that can happen here though. So what would we say our answer is? 5 pi over 3. Now this would be in centimeters because we're talking about this outer edge here. Okay, now this would be considered the exact answer. So if you remember in the past on some worksheets like with area and like perimeter and that, especially when we dealt with circles or like cones and cylinders, anything that had a circle in it had pi. A lot of times on your homework, you'd see like a little line and it would have that E in parentheses after that. Do you guys know what I'm talking about? On your homework, you'd have something like this. And that would tell you like leave it in an exact form. So don't calculate with pi. If you see that today, then just leave your answer there, 5 pi over 3. Now, if they don't have the E, that means that if you would like to, you could actually calculate this with pi and write it as a decimal. To do that, you would just take on your calculator 5 times pi. And you can either use the pi button or you can use 3.14. So take that, multiply each other first, and then divide by 3. Can someone do that? Someone take 5 times pi, divide by 3, and tell me what we get. Let's round it to the nearest tenth. 5.2 centimeters. Okay, I'm going to take either answer, like when you're doing this on your test on Friday. I don't care if you give it to me in the exact form, if you give it to me as a decimal. Now, if the problem specifies how they want it, then make sure you put it in the right form. If they say exact, I'll just put here, this would be the exact answer. The 5.2 would be an estimation because it's calculating with pi, which is an irrational number, so we're rounding it, we're cutting it off. That's not an exact answer anymore. Now it's an about answer. It's about 5.2 centimeters. Okay, but pay attention to that on your worksheet today because there are some, I think like the majority of the front side of the worksheet wants it in exact answers, but then the back side kind of gets rid of that E and you can start writing it with a decimal if you need to. Why don't you guys try that second one here on your own? All right, for this one, what did you guys put in for your theta? Pi over 2. And what goes in for the radius? 16. Can you do any reducing? Yeah, what can we take out?
2 and 16.
So the 2 becomes a 1, the 16 becomes a 8. So what do we get here?
8 pi.
8 pi. Good, centimeters. Or, anyone have the decimal for me?
25.1 centimeters.
Good, 25.1 centimeters would also be okay if they were not asking for the exact answer. Again, just pay attention to what they want. If it says exact, then just stop at 8 pi. Okay, now sometimes they may not give you pictures. Like that one had 2 diagrams. It had everything that you needed. You just popped it into your formula. You simplified. Okay, there's going to be times now where we don't have a picture, so we have to read the information to figure out what do we have and what goes where. And you might start to run into problems where they don't give you theta and the radius. Maybe instead they give us the arc length and we need to find theta, or we need to find the radius. Okay, so we'll have to maybe be able to work with this formula a little bit and move things around in order to help us solve for whatever they're asking for. So if you go to the next one here, this one doesn't have a picture. It's just describing what's going on. It says, what is, well, there's actually quite a few typos in this. What the length? I think they mean what's the length of the arc. So what's the length of the arc if the circle has a radius of 10 centimeters and the central angle is 4 pi over 5? So I'm still thinking about this formula. Arc length is equal to my central angle times the radius. What can we plug in for which piece here? What is the 10 centimeters going for? The radius. What does the 4 pi over 5 going for? The theta, the central angle. Okay. Any reducing that you guys see we can do? 5 becomes a 1, 10 becomes a 2. So what are we left with here? 8 pi centimeters, or we just did this, 25.1. It's the exact same answer as what we got on this last one here, but notice how the central angle is different. It's not the pi over 2 anymore. It was 4 pi over 5. This could just be in a different area on the circle then. So it's not talking about maybe that first quadrant. Maybe it's on a different quadrant, or it's just kind of at a random angle inside that circle. Okay, let's take a look at the next one. Find the measure in radians of a central angle that intercepts an arc of length 4 pi centimeters in a circle of radius 10 centimeters. So again, I'm thinking about my formula here. What can we put in where? R is 10. What does the 4 pi represent? S. How did you know that? Is there something that kind of signified that to you?
It says arc of length is 4 pi.
Yeah, arc of length. So that's basically just saying the arc length, the S, is 4 pi. So that's how we know it needs to go in for S, not for theta. They're also asking, if we even just go back to the beginning, find the measure of a central angle. So they're asking for that piece. That's what's missing. So that's why we don't have anything plugged in for theta. How would we solve this? Divide by 10. Theta right now is just like a variable. So think of it almost like x times 10. You just want to get that x by itself. So these 10s are gone. How does this reduce? Let's keep it as a fraction. How would 4 over 10 reduce? 2 over 5. So my theta would be 2 pi over 5 radians. Not centimeters this time, because it's talking about that central angle. So an angle is going to be measured in either degrees or in radians. In this case, because it's got the pi, we're keeping it in radians. If they wanted it in degrees, then you'd have to go back to what we did yesterday. You'd have to multiply by 180 over pi in order to get it to degrees. Questions on that one? Okay, we've got one more. So this last one here is talking about these two pulleys and how they lift a weight. So the weight, like the rope that's holding it, wraps around the circumference of the circle as the weight gets kind of pulled on. It says that if a pulley with a radius of 10 centimeters is pulled with an angle of rotation of 45 degrees, how high will the weight rise? I'm still thinking about my formula that we started off with here today. S is equal to theta times the radius. Do they give me the radius? What is it? 10. It says right here, radius of 10. So that's going to go in for your R. Okay, now if you follow over here, it says angle of rotation of 45 degrees. When I'm working with this formula, have we had any problem so far with this theta times R where I plugged in degrees? What have I been plugging in? Not degrees, but radians, right? So I need to maybe make 45 degrees become radians. Now let's think about how we could do this. Some of you can look at what we did yesterday. Okay, we talked about this kind of the beginning of the unit circle. If you look at that circle right there, where would 45 degrees be? Between 0 and 90, halfway between, right? It'd be the exact middle of whatever this section is. So if I started to slice this even smaller, 45 would be right here. Now, if 90 is pi over 2, anyone have an idea how we could write 45 degrees in radians? What would be half of that? It'd be pi over 4. Okay, if I knew that this was 45 degrees, this would be half of pi over 2. Well, half of a half, or think about if you had half like 50 cents, half of 50 cents is 25 cents. So it'd be a quarter. So that's where that pi over 4 comes from. Okay, now if you can't think that way, or if it starts to get really bizarre, okay, like if they said 30 degrees or 20 degrees, that's a little bit harder to think about fractionally. How would you get from halfway to 30 degrees? We can do what we did yesterday. Remember, to change something to radians, you take 45 times pi over 180. This is what we did yesterday in class. The 45 can go into 180 4 times. And so what you're left with here is pi over 4. You get the same answer that we did when we were just thinking about that unit circle. But this time I was actually doing that conversion like we practiced yesterday. So if you get to a degree, you could use that original formula that I gave you way back at the top of this page here. You could use this formula right here if you wanted to. Okay, but we've been so used to using theta times radius that it might be easier if we just kind of stick on that track so you don't have to try to remember all these different formulas in your head. So instead, over here, I'm going to plug in pi over 4 for theta. Is there any reducing that we can do here? What can we do? 4 becomes a, and 10 becomes a 5. So what am I left with here? 5 pi over 2 centimeters. Okay, or what would be the decimal? So if I round it to the nearest tenth, it'd be 7.9?
Yep.
centimeters. Any questions on that last one? Okay, I'm going to get you guys your homework. You'll have the rest of class here to be working on that.